Let's imagine we want to improve an existing in-cloud solution based on SAP Cloud for Energy, or C4E in short, for an energy operator with the aim of providing an AI-based tool to accurately predict the energy demand of consumers in a certain area of the city of Berlin. We know SAP Cloud for Energy is an SAP cloud solution that works as an IoT hub for energy meters. Energy meters can be directly connected and stream data to SAP Cloud for Energy. Their meter data can be stored, cleansed, and validated. C4E communicates with S4HANA for utilities, which holds customers' master data, smart meter master data, etc. And it is responsible for the billing. C4E can be the data source for several solutions with the traditional in-cloud architecture. From C4E, one can monitor the several connected devices from specific views and inspect also their details based on the relative master and reference data. For instance, the smart meter information per city, model, their status, etc. From C4E, it's also possible to view the measurements of the individual smart meters. For example, let's select 4 in the city of Berlin and let's take a look at the acquired data. C4E currently allows to store aggregate domestic consumption at the rate of 1 measurement every 15 minutes, as we can see from the dashboard here. This is good enough for many applications, but in our case, we want to take advantage of the high data granularity of our devices to produce more accurate predictions of the consumer energy demand without moving the data from where it is produced. To do this, we have introduced a third-party IoT platform to manage the runtime of the smart home devices and also to enable the communication with the cloud and in particular with BTP. We chose Azure IoT platform, but it can be any other platform. There we created an IoT hub and registered the 4 devices located in Berlin that are connected also to C4E. Our smart meters are equipped with a running runtime and are able to run some code. We have developed to wrap a machine learning model that is able to produce demand forecasting based on the household energy loads and weather data, and that we trained in SAP AI Core. Moreover, the code is also able to manage the needed communication with the cloud to receive the needed input data and send back the predictions. And indeed, the smart meters receive data in the form of messages from the cloud, as we can check from the IoT Hub dashboard. These messages contain weather data needed for the demand forecasting. Let's take a look at one of them. We see that we are passing an array containing information such as temperature and humidity conditions in the last 24 hours, etc. But under the hood, this is possible because we have implemented and scheduled at midnight a specific cloud-to-edge pipeline in AI Core to fetch the weather data from a third-party service and send this information to all devices connected to the IoT Hub. We can see in AI Core the schedule created for this pipeline and the past executions attached to it. We can open one and check the logs to see that the pipeline is configured to consume a connection string to the IoT Hub and send data to all the 4 attached devices. As already mentioned, based on the energy loads and weather data, the model used in the 4 smart meters produces a forecast of the energy demand for the next day for each household. We can check the logs of the code that performs the inference phase in the smart meters and take a look at one of these results. What we can see is that the result contains the energy demand forecast for each hour of the next day, and that is immediately sent back to the IoT Hub and then routed to the object store, which in this case is the Azure Blob Storage. There, the energy demand forecast for each house is saved in the form of a JSON file. The JSON files for all the 4 smart meters are then retrieved and brought into BTP thanks to another pipeline that is executed in AI Core and that will complete the edge-to-cloud data flow. This pipeline is executed once a day after the execution of the one previously described, and that takes care of the cloud-to-device communication expected at midnight. If we check the logs of one execution of this pipeline, we can see that the pipeline connects to the Azure Blob Storage, downloads all the JSON files for the current day, and writes the energy demand forecasts for all the devices in DataSphere. At this point, the data is ready to be further consumed within BTP, for example, within SAC via a live connection. SAC is the simple choice for creating a dashboard for an energy planner. We can see here a very simple example of how the energy demand forecasts can be used to build meaningful graphs for an energy planner. Firstly, it's possible to show the total energy demand forecast for the next day, hour by hour, with the possibility to inspect each IoT hub that covers basically different geographical areas. The energy planner, for example, can compare this data with the energy that will be supplied for the following day. And in case of discrepancy, he can take action. The energy planner can also check the energy demand forecast for each of the devices connected to a specific IoT hub. Please note that this is also the information needed to feed an energy distribution optimization algorithm that can be used to determine how much energy to send to each prosumer a day in advance. As a final observation, please note that since we have established a live connection between DataSphere and SAC, the data shown in the dashboard will be automatically updated every day or whenever a new forecast is requested and the edge to cloud data flow takes place.